keep in your chairs. Now we will fly to Colombia chapter, and let me give the panel to Colombia representing Mr. Gonzalo Gallo. Welcome.
Hello, and thanks for that introduction. As always, a pleasure to see a talk from the Iraqi chapter, and thanks to ACI for organizing this event. From the Colombian chapter, we have participated in this for over 5 years. I mean, every time, and we're always happy to be with you guys. Our chapter has about 300 members, and we do a lot of events. And this is one of the key components of our normal schedule of things. Again, we just want to expand the knowledge on concrete. So to keep things in time, we have 2 presentations today as other chapters. And the first one is given by Andrés Guzmán. He's an ACI member, professor at Universidad del Norte in Barranquilla here in Colombia. He received his BS in civil engineering from the Universidad Nacional in Colombia and his MS in structural and seismic engineering and his PhD in biochemical engineer from the Universidad Los Andes in Bogota. He's the faculty advisor for the ACI student chapter at his university and member of committees such as 242, Alternative Cements, 314, 357 for offshore and marine structures, and he's an ACI faculty network committee 88. His research interests include the advanced materials for concrete construction, the development of high-performance concretes with locally available resources, the use of alternative cements, offshore and marine concrete structures, and sustainable design practices. The talk that he's giving today is called Bond Behavior of GFRP Bars in Conventional Ultra-High Performance Concrete. So with no further ado, Andrés' presentation.
Hello, everyone. My name is Andrés Guzmán, and I am pleased to introduce this presentation on behalf of my graduate student, Alberto Vázquez, who is working under my guidance and under the guidance of Professor Joaquín Avellán. We are both professors at Universidad del Norte in Barranquilla, Colombia. We will address the bond behavior of glass fiber reinforced polymer, GFRP bars, when embedded in conventional and ultra-high performance concrete matrices. This presentation summarizes an experimental study investigating how concrete strength, ranging from 20 to over 120 megapascals, affects the bond with GFRP bars. The results have implications for design and durability. Thank you to the American Concrete Institute for the opportunity to present this work today. The use of GFRP bars has expanded rapidly, especially in marine environments, on bridges, and at desalination facilities due to their excellent corrosion resistance. However, their interaction with concrete, especially the development of bond strength, remains unclear, particularly with high-strength concrete. Most existing tests, such as pull-out methods, fail to capture the actual stress present in flexural members. Additionally, current codes offer little guidance on using advanced concrete, such as ultra-high performance concrete, UHPC. To address these gaps, we employ the Ryland RC5 beam test method, adapted specifically for GFRP bars. This method offers a more accurate representation of structural behavior under service conditions. This methodological refinement paves the way for evaluating the influence of compressive strength on bond and its implications for future design criteria. This side-by-side comparison shows that although steel bars are ductile and widely accepted in code-based design, they suffer from corrosion and conductivity issues, especially in tough environments. GFRP bars, on the other hand, offer outstanding corrosion resistance and are non-conductive, making them ideal for specific applications. However, their low stiffness and brittle behavior introduce unique challenges. These differences make bond performance crucial, particularly when designing with high-strength or ultra-high performance concretes. This figure compares the typical stress-strain behavior of steel and GFRP reinforcements. The GFRP curve on the right exhibits a linear elastic response up to failure with no yielding, resulting in a brittle rupture around 1200 megapascals. This behavior is governed by its lower modulus of elasticity of about 60 gigapascals and the absence of plastic deformation. In contrast, the steel curve shows a well-defined yield plateau beginning at a strain of 0.002, followed by strain hardening beyond 0.025. This ductile behavior allows for energy dissipation and is central to traditional design approaches. This diagram summarizes the structure of our research. At the core is our central question: how does the compressive strength of concrete affect the bond performance of GFRP bars? To answer this question, we designed a series of self-consolidating concretes, SCC, with strengths ranging from 20 to 80 megapascals, as well as an ultra-high performance concrete, UHPC, exceeding 120 megapascals. We then tested each of these mixtures using the Riley RC5 hinged beam method, which provides a more realistic simulation of surface conditions than traditional pull-out tests. We analyzed bond slip curves to evaluate maximum bond strength, stiffness, and post-peak behavior. Then, we compared these results to the code-based prediction from ACI 440 and CSAS 806 in the evaluation of the accuracy of or conservatism of the current design models. Finally, we translated our findings into practical design recommendations useful for the structural applications involving GFRP reinforcement in high-performance concretes. The bond between GFRP bars and concrete is traditionally tested using the ASTM D79 pull-out method. Although this setup is standardized and widely used, it creates stress conditions that differ from those experienced by real structural models. Typically, it applies a uniform axial pull to the bar, failing to account for flexural behavior, cracking patterns, or confinement effects. To address these limitations, our study adopted the Riley RC5 hinged beam test method, which was originally developed for the steel rebars but was adapted for GFRP in this study. This configuration induces a pure bending moment, producing a bond slip response under more realistic surface conditions. This diagram illustrates the configuration of the Riley RC5 hinged beam test, which was adopted for our study to evaluate the bond behavior between GFRP bars and concrete. The specimen is 65 centimeters long specimen and is a prismatic beam supported at both ends by movable supports that allow rotation and simulate flexural action. The GFRP bar is embedded along the beam's axis. However, the central region, spanning over 10 times the bar's diameter on each side, is intentionally debonded using plastic sleeves. This localizes bond activation in the central bonded zone. A central point load, Fa, is applied to create a pure bending moment at midspan. This generates tension in the bar and bond stresses that more closely resemble real structural conditions than pull-out tests do. A slip is measured at the bar ends using LVDTs, and failure is typically governed by bond strength or pull-out from the bonded region. This configuration enables us to capture the bond-slip relationship, peak bond stress, and post-peak behavior more accurately. The experimental program included 4 concrete mixtures that covered a wide range of strengths, from conventional self-consolidating concrete, SCC, with a compressive strength of 20 megapascals to ultra-high performance concrete with a compressive strength exceeding 120 megapascals. The goal was to isolate the effect of concrete strength on the bond with GFRP bars while keeping all other parameters constant. We used sand-coated B-Road 60 number 3 bars for the reinforcement, which are widely used in corrosive environments. All beams were cast using wooden molds with plastic sleeves installed to define the bond region following the Ryland RC5 geometry. These carefully controlled conditions ensured consistency across specimens and reliable comparison of results. This table summarizes the mixed designs used in the experimental campaign. 3 self-consolidated concrete mixtures with increasing compressive strengths of approximately 20, 45, and 80 megapascals were produced through progressive reduction in the water-to-cement ratio and adjustments in fine aggregate content. A 4 mix corresponds to ultra-high performance concrete and was designed with a water-to-binder ratio of 0.18, a high cementitious content, and the addition of silica fume, fly ash, and 2 types of steel fibers. Notably, the UHPC mix eliminates coarse aggregate, relying instead on particle packing and fiber reinforcement to ensure mechanical performance and matrix densification. All mixes were proportionate by mass per cubic meter to ensure proper casting in Ryland beam molds. These images illustrate important aspects of preparing specimens for bond tests. The first photo shows the wooden molds used to cast the Ryland RC5 beams. The GFRP bars are placed longitudinally with plastic sleeves in the central zone to create unbonded regions and ensure bond activation only within the designated embedment length. The second image shows the steel reinforcement cage used to simulate confinement. It contains 6.4 and 8.5 mm diameter rebars that are placed strategically to replicate the presence of transverse reinforcement and the shear effects observed in real structural elements. The third image displays the expanded polystyrene inserts used to form the central hinge. This feature ensures a clean fracture plane and consistent bending behavior during testing. All specimens follow this setup to maintain experimental consistency and simulate service-like stress conditions. This slide illustrates the control mixing sequence for both SCC and UHPC mixtures. First, we introduce all cementitious materials, including cement, silica fume, and mineral additives. These materials were dry mixed to ensure homogeneity. Next, we gradually added the mixing water and the high-range water reducing admixture. This stage starts hydration and enhances the dispersion of fine particles. As shown in the third image, an initial reaction is triggered at this stage, resulting in visible clumping because of the interaction between the silica fume and the water. Then, we added the sand in increments to ensure uniform distribution without overloading the mixer. Finally, we slowly incorporated the steel fibers into the fresh matrix to minimize agglomeration and maintain workability. This standardized procedure was essential for achieving consistent rheology and strength across all batches, particularly for the ultra-high performance mix. This slide summarizes the casting and curing process for the Ryland beams and cylindrical specimens used to evaluate compressive strength. The first sequence shows the casting phase in which fresh concrete is placed into the beam molds and standard cylinders. Proper vibration and surface finishing were used to eliminate voids and achieve uniform consolidation. The second sequence shows the curing process. All specimens were stored under controlled humidity and temperature conditions for 28 days under ASTM C192 guidelines. This step was critical to ensuring the development of full mechanical properties, especially for the UHPC mix. After the curing period, the formwork was removed. The beams and cylinders were then demolded and prepared for subsequent testing, including bond strength and compressive strength assessments. This entire protocol was strictly followed to maintain consistency and reproducibility across all concrete batches. This table summarizes the compressive strength results obtained from standard cylinder specimens tested at 28 days for each concrete mix. The target strength, known as design FC, ranged from 20 megapascals for the lowest strength self-consolidating concrete mix to 120 megapascals for the ultra-high performance concrete mix. In general, all mixtures met or exceeded their design strength targets. For instance, SC20 achieved an average strength of 18.65 megapascals, which is within acceptable variation for low-strength self-consolidating concretes. The SC45 and SC80 mixes achieved average strengths of 46.69 megapascals and 79.22 megapascals respectively, indicating good consistency and alignment with mixed design expectations. The UHPC mix reached an average strength of 122.72 megapascals with minimal dispersion across specimens, highlighting the effectiveness of matrix densification and fiber reinforcement. This result confirmed the reliability of the casting and curing process and validated the use of these mixtures for the bond testing program. They also provide a reference framework for interpreting the bond behavior observed in each mix type. This slide illustrates the full setup of the Ryland RC5 hinged beam test, which is used to evaluate the bond behavior of GFRP bars embedded in concrete. On the left side is the specimen geometry. Two symmetrical concrete beams labeled A beam and B beam, joined by a central steel hinge. During casting, a block of expanded polystyrene was temporarily inserted to create the hinge void. After curing, the placeholder was removed and replaced with a steel hinge, which allows for free rotation and induces a pure bending moment at mid-span. A single GFRP bar runs continuously through both beams and is partially bonded over a defined length, and the bond region is carefully controlled using plastic sleeves that isolate the bonded segment. On the right is the complete test setup in the universal testing machine. The specimen rests on roller-type supports that allow longitudinal movement and ensure a true hinge condition. A loading head connected to a calibrated load cell applies the load vertically at the hinge, enabling precise force measurement. This configuration produces a well-defined bond stress state that simulates real structural conditions more effectively than conventional axial pull-out tests. This slide presents the visual results of the bond strength tests conducted on GFRP reinforced specimens using the Ryland RC5 configuration, alongside the formulas used to calculate the bond stress. On the left of each pair, we observed the unloaded, undamaged beams in the testing frame. On the right, we see the condition of the same specimen after failure, revealing the distinct failure mechanisms associated with each mix. In the top row, the SC20 mix, a low-strength self-consolidating concrete, exhibited progressive bond slip with surface cracking and limited concrete crushing. The middle row shows the SC45 mix. Here the failure became more localized, with sharper cracking along the bond and some separation between the beam halves. The bottom row corresponds to the UHPC 120 specimens. These showed a markedly different behavior, a brittle failure mode, dominated by interface debonding with almost no surface damage, a result of the high matrix stiffness and densification. Although the SC80 mix is not shown, it presented an intermediate behavior, with moderate cracking and improved bond capacity relative to SC45, but not as abrupt as in UHPC. On the left side of the slide are the expressions used to calculate bond stress tau, which are derived from the applied load Fa and the nominal bar surface area An. The constant 40 in the denominator reflects an assumed anchorate length of 10 times the bar diameter, providing a uniform stress distribution model as per Ryland standards. Altogether, this comparison highlights how both material properties and structural configuration govern the bond performance of GFRP bars in high-performance concretes under bending conditions. This slide compares two common approaches to estimating the bond strength of GFRP bars, the ACI 440.1 equation and the CSA S806 equation. Both approaches are derived from pull-out test data and estimate bond strength based on concrete strength and bar geometry. The ACI approach is more empirical, whereas the CSA model incorporates adjustment factors for bar location, concrete type, and surface condition. However, as our experimental results show, both methods tend to underestimate the actual bond strength measured by the Riley RC5 hinged beam test, especially with high-performance concretes such as UHPC. This underscores a critical limitation. Standardized pull-out tests do not replicate the flexural stress conditions experienced by real structural members. By contrast, the Riley method provides a more realistic and often higher estimate of bond performance, which may be essential when designing with advanced concretes and GFRP reinforcement. As expected, the SC20 mixture exhibits a soft ascending curve with a lower peak bond stress followed by gradual slippage. This reflects limited confinement and weaker matrix resistance. The SC45 and SC80 mixtures demonstrate higher bond strength and stiffer responses. Their curves rise more steeply, reaching higher peak values before dropping abruptly, indicative of partial interface failure. The UHPC 120 curve is different. It shows a steep linear rise and a sharp drop after the peak, which is typical of brittle debonding. Its extremely dense matrix provides strong mechanical interlock but minimal energy dissipation once slippage begins. These curves confirm that bond performance depends heavily on concrete compressive strength and matrix structure, and that UHPC presents unique design considerations due to its brittle failure mode. These findings are critical for defining development lengths and anchoring strategies for GFRP reinforced elements in high-performance concrete. This slide presents a combined view of the bond slip behavior of GFRP reinforced specimens and the corresponding bond strength predictions based on different design standards. On the right, we observe the experimental bond slip curves obtained using the Riley RC5 test, which captures the service-like bond behavior under bending. As seen, bond strength and post-peak response varied significantly across mixtures. The table on the left compares the measured bond strength tau from Riley testing with estimates derived from the following design standards: ACI 440.1, which is based on pull-out behavior, CSA S806, which provides more conservative guidance, and ASTM D7913, a standardized pull-out test method. A key observation is that all normative methods yield significantly lower bond strength values compared to the Riley results. For example, in UHPC, Riley testing measured 23.04 megapascals, while ACI predicted only 13.82 megapascals. This underestimation is consistent across all mixtures and highlights the limitations of existing standards when applied to high-performance concretes or when bond is mobilized under flexural stress states. The results suggest that Riley RC5 provides a more realistic assessment of in-service bond performance, especially for design cases involving UHPC or advanced self-consolidating concrete mixtures. Therefore, for accurate anchoring design and reliable development length estimations in GFRP reinforced members, project-specific testing or revised code provisions may be necessary. This table and graph summarize the average compressive bond and slip strengths of each concrete mix tested under the Riley RC5 configuration. As expected, there is a strong correlation between compressive and bond strengths. The SC20 mix produced a bond strength of 15.25 megapascals with a measured strength of 18.65 megapascals. Bond strength increased to 21.5 megapascals in the SC45 mix, around 41% increase compared to the SC20 mix. This confirms the positive effect of improved matrix cohesion. Although the compressive strength of the SC80 mix nearly doubled compared to the SC45 mix, the bond strength increased only marginally, reaching 22.09 megapascals. a 2.75% increase over the previous mix. This suggests a point of diminishing returns for bond development in traditional self-consolidating concretes. In contrast, the UHPC 120 mix achieved the highest bond strength of 26.33 megapascals, a 72.7% increase over SC20. However, this was accompanied by a significant increase in slip, reaching nearly 10 millimeters. This indicates brittle post-peak behavior. These findings emphasize that while compressive strength enhances bond capacity, matrix characteristics and failure mode, particularly in UHPC, play a critical role in how the bond is mobilized and dissipated. In conclusion, the results of this study demonstrate that the bond behavior of GFRP is significantly impacted by the concrete matrix, particularly its compressive strength and internal structure. Although UHPC offers superior bond strength, it also exhibits brittle debonding behavior that must be considered in the design process. The RILEM RC5 test method proved valuable for simulating realistic stress conditions, producing bond values that exceeded those predicted by ACI, CSA, and ASTM pull-out-based provisions. This discrepancy underscores the need to update or supplement current design standards, particularly when working with advanced concrete technologies. For practicing engineers, this finding suggests that using RILEM-based bond models or conducting custom bond testing is essential when designing with GFRP in self-consolidating concretes or ultra-high performance concretes. Ultimately, incorporating more representative testing methods into design practices will result in safer, more efficient, and better optimized GFRP reinforced structures. That concludes the presentation. Thank you for your attention and interest in GFRP bond behavior in advanced concrete matrices. I would like to thank the American Concrete Institute and the organizers of the 24 Hours of Concrete Knowledge event for this opportunity to present our work. I would also like to acknowledge the technical and material support we received throughout this research. Special thanks to Ultracem for providing cement and admixtures, Aripreg SA for the GFRP reinforcement, Beckert for supplying steel fibers, Sika for the super plasticizers used in the self-consolidating concrete and the ultra-high performance concrete mixes, Grupo HA for designing and fabricating the mechanical hinge used in this testing. I would also like to express my gratitude to the Civil Engineering Laboratory at Universidad del Norte and to Alberto Vázquez, our hardworking graduate student, for his dedication to the experimental campaign. If you have any questions or would like to follow up, please feel free to reach out. My contact information is available here. Thank you once again, and I look forward to continuing the conversation on how GFRP and high-performance concretes can advance structural design.
Thanks to Dr. Guzman. I think there's perhaps just a single question we can answer, and then I understand he'll be writing all the answers on the chat. I see several of them, but maybe you can expand on the GFRP behavior compared to steel, which is one of the first questions that we got on the chat, and then all of them will be answered.
Thank you. Thank you, Gonzalo.
So yeah, if you could answer just the one on GFRP yield in comparison to steel.
Yeah. This is a very interesting question because there is a feeling about the behavior of these kind of bars. It takes an excellent point because unlike steel, the GFRP bars are linearly elastic up to failure, and it's a brittle failure. There has no yielding or plastic deformation, so there is no warning before ruptures as the steel reinforcement, and there is a suddenly failure. So we need some visual indicators like cracking in the concrete because you have to inspect or monitor the crack width, the spacing, or maybe try to follow some deformation patterns because there's different failure mode compared to the steel rebar. So we have to make a shift in our design philosophy where crack control and stiffness-based criteria are more prominent for these kind of systems.
Thank you once again for your time and answers. And of course, as Dr. Guzman explained, he's ready for every answer or questions you might have afterwards, or if you want to reach him, his information was on the presentation. Continuing with our speakers, the next one is probably known by many of you. Our next speaker is Carlos Arteta. He won a prestigious award last year from ACI. He's an associate professor also at the Universidad del Norte in Colombia, member of ACI Committee 318, and he's part of the subcommittee H, for which works for seismic provisions. He has founding president of the CER, Colombian Earthquake Engineering Research Network, member of board of directors of ACI Colombia, which I have the honor to be a part of. And his research interests include the response and design of buildings to earthquake actions, with expertise in analysis, design, and risk evaluation of reinforced concrete structural systems. Today, we'll see a talk on entitled From Design Drift to Damage, Repair Periods for Repairability Loss in Special Moment Frames. So this is Dr. Arteta and his presentation.
Hi, my name is Carlos Arteta and I am an associate professor in earthquake engineering at Universidad del Norte in Colombia. I also serve as an ACI 318 and 374 member, and currently I am the vice president of the Colombian chapter of ACI. Today I will be presenting a work in progress I've been doing with my student Nicolás Quintero and with Professor Tayo Opabola at UC Berkeley, titled From Design Drift to Damage, Return Periods for Repairability Loss in Reinforced Concrete Special Moment Frames. The goal is to estimate the return period at which reinforced concrete special moment frames designed with different drift limits remain within acceptable damage control performance thresholds. As a motivation, we have the recent work led by Professor Opabola about repairability limit states for ductile reinforced concrete structures. With regard to SMF, some key takeaways from their work is that reinforced concrete special moment frames are designed for large strips only to meet life safety goals. Well, this decision may exceed repairability thresholds, leading to costly damage as observed during the Christchurch sequence in New Zealand. So when we have a reinforced concrete moment frame undergoing lateral shaking, we expect that the beam ends and column ends go plastic deformation, so we can define the beam rotation beyond repairability as the onset of lateral strength loss, for example, when the onset of bar buckling is observed. For ductile reinforced concrete beams, the median LSL rotation is about 3.6%, so here for this study we set a 2% rotation limit to cap the probability of exceeding LSL at 20%. To achieve our goal of estimating the return period of EDPs in a building, we need to select a ground motion selection technique. In this case, we select the conditional scenario spectra, which is a hazard-consistent ground motion selection technique that is able to pick realistic ground motion spectra, meaning that they have the correct spectral shape for different intensity levels. And with this characteristic, it is able to reproduce the hazard at a site over different return periods and different oscillators periods. So this is an example of how the ground motion selection looks like for return periods from 500 to 4,000 years. And on the left-hand side, you can see the scenarios that went into the selection. The main idea of the CSS is that we can assign the rates of occurrence of each each one of these ground motions to the EDPs, and in this case we are showing how the ground motion set that comprises about 300 ground motions is able to recover the hazard at a site. In this case we are talking about Treasure Island in the Bay Area of San Francisco. With the CSS rates of occurrence, the EDP risk can be estimated to understand when an EDP level matters or is of concern. The EDP risk curves relate the EDP levels to their corresponding return period. For example, in the left-hand side figure, we have that the return period of the 1% roof drift ratio of a reinforced concrete frame is 2,800 years, which may be rare enough as not to be of concern, but that depends on the risk we want to accept as society. Well, here we have the Treasure Island site location, and it is important to mention that the frames we are about to analyze were designed according to ACI 31819 for special moment frames, considering loading from ASCE 2022. Here we present a contrast of the DBE and MCE ground motion levels versus the discretization of the hazard as represented by UHS. This is important because for different periods of the structures, the MCE and the DBE levels have different return periods, which are gathered from this type of figures. For the conception, the linear and the nonlinear dynamic analysis, we utilize the platform RCFIAP developed here at Universidad del Norte. So RCFIAP is able to conceive and design a frame according to code and automatically create a nonlinear model of the building. The two types of analysis were performed on the study frames. One were pushover analysis, where we can see the plausible collapse mechanisms and notice that they were dominated by a beam mechanism, which is of interest for this particular investigation. And we were also able to perform several nonlinear dynamic analyses to gather EDP versus rate pairs to be able to construct the risk curves of two EDPs of interest. One were the story drift ratio, and the other one was the maximum beam end rotations. So this second EDP is of main interest because we claim that a building is well behaved if the beam rotations are not large enough as to surpass the 2% drift or rotation limit that we defined previously in this investigation. So here we have the first example. This is a 6-story frame, and this number goes down to about 1,000 years for the building designed for a 2% story drift ratio limit. In any case, the return periods are above DBE, which might be satisfactory or not, depending on the risk level that the owner wants to accept. In all cases, except for the the stiffer building, these return periods are below MCE. Next, let's move on to the 10-story building. As you can imagine, the columns and the beams become more robust if we want to impose those story drift limits for design. Below you have again the pushover curves of the buildings under analysis, and here we have again how the drift or the return period of the 2.5% drift demand behave. Again, we can see that the response is similar or follows a similar trend to the behavior of the 6-story frame, but now the return periods are closer to DBE. Meaning that if we go below DBE, it becomes more likely that the 2.5% story drift ratio will be observed in the building. When we compare both frames in terms of beam rotation or the rotation beyond reparability, we see that they follow the same trend, but the 10-story building designed for 2% story drift ratio limit achieve or exceeds the reparability limit stays close to DBE. So as we are showing in this presentation, the analysis under the CSS, which is a hazard consistent growth motion selection techniques, allows us to ask different questions from the traditional manner of response analysis. Now we can answer when it matters, and we are seeing that these two particular frames seem to be safe independently from the story drift limit imposed during design, but definitely the buildings from design for 1.5% and 2% behave almost or similarly, and you really need to stiffen a lot the building to change the return period beyond reparability. So the conclusions of this work are that the design story drift ratio significantly impacts the return period of the maximum beam rotation. The risk of both frames is comparable, as we just showed in the last figure. Here, for example, the beam rotation beyond reparability is about 1100 years for the frame with 1.5% drift limit for design, while it goes down to about 850 years for the frame design with a 2% story drift ratio as limit. Importantly, what we learned from here is that the return period of the EDP, in contrast to the DBE and the MCE levels, must be done on a case-to-case basis as it is a period-dependent problem. So thank you very much, and I hope you enjoyed this talk.
Well, thank you to Dr. Arteta and his great presentation. I think it's an ongoing study, as he explained, but with very promising results of understanding the behavior of these buildings. I don't see many questions on this regards, Bernie. I don't know if you have any particular from other attendees.
Well, let me see what I have here. I have, it looks like I might have one. It says, yeah, there's both the 6 and 10-story RC moment frames in your study showed return periods for 0.5% SDR exceeding the MCE level. Given that these are moment frames, do you think excessive initial stiffness contributed to this? And beyond over-design costs, could such stiffness also reduce ductility or hinder effective energy dissipation during larger seismic events?
This is a very good question, but as we usually academics do, we come up with some designs. In this case, the 0.5% story drift ratio building. If you check the size of the members, they are 1400 millimeters by 1400 millimeters, which might be prohibitive in terms of cost, right? But yeah, importantly, to answer the question is that we are checking the building at relatively low story drift ratios, in this case at 2%. So we are not pushing them up to collapse to understand or to try to see if what the viewer is or the concern of the viewer is materialized. So at this point, we stop very, very early at 2% or about 2% story drift ratio. So definitely longer members will have a lower rotation capacity, indeed less ductility, but this is not part of the study.
I do see an additional question, Bernie. It says, Using break walls under the beams, I guess the question is, can this reduce the risk?
Can you repeat the question, Gonzalo? Sorry, I'm sorry.
The question states, using break walls under beams reduce the risk. I'm guessing if using walls, shear walls, maybe not break walls, this can reduce the risk of the rotation.
Definitely, but it will enhance the problem of the previous question, right? Longer members will have a lower rotation capabilities. But at this moment, we are doing the study of a 6 and a 12-story building with the special reinforced concrete walls as lateral load resistance system. We don't have the results yet in terms of risk, but maybe in the next presentation, we will be presenting this in ACI 374 in the next convention in the fall for sure. But at this moment, we're just running the models. Each model takes like 55 hours to run, so it's still in the making.
Awesome. Well, we're eager to see the results this fall. Well, Bernie, I don't see any further questions. I guess we have a little time for ACI.
I just want to make a little comment here is that, I mean, it seems the days of poor recordings and sketchy films is gone. Maybe I'm talking too soon, but it's much improved the quality of our videos and the presentations. And I want to commend, Carlos for working at it, because I remember we had a problem a couple of years ago. And
2 years ago, Bernie, but it's fine. It worked well at the end.
Yeah, this is perfect right now. I say it's a top first class.
Thank you. We're learning.
Okay, thank you.